Rhys Evans, who is now postdoc at Sobolev Institute of Mathematics, and I'm really happy to have his thesis with us. So he continued to talk on Neumaier graphs.
Okay. Thank you. Thanks for having me as well. And yeah, I will continue talking about Neumaier graphs and maybe about some more open questions that have yet to be tackled. I must say, if the start of Martin's talk was an insult, I don't know what kind of sin I'm going to commit now, but please let me go back over some definitions. So an edge regular graph with parameters v, k, lambda is a graph with v vertices, at least one edge, which is k regular, and each pair of adjacent vertices share lambda common neighbors. And a strongly regular graph with parameters v, k, lambda, mu is an edge regular graph with parameters v, k, lambda. It has at least one pair of non-adjacent vertices, and each pair of non-adjacent vertices have exactly mu common neighbors. Excuse me. And a clique is regular if every vertex outside of the clique is adjacent with the same number, which I will denote instead of v as m vertices inside the clique. And m is called the nexus of the clique. The clique is called m regular. So here's a 2 regular 8 clique. And as Martin says, Neumaier in the 80s was working with edge regular graphs containing regular cliques in relation with certain finite geometries. And in particular, he proved this theorem saying that a non-empty graph, which is vertex and edge transitive, that also contains a regular clique, is either complete or strongly regular. And this motivated him to ask the question, is there any edge regular graph with a regular clique, which is not strongly regular, or is every edge regular graph with a regular clique strongly regular? So that's where the definition comes from. So a Neumaier graph is a graph which is edge regular, non-complete, and that contains a regular clique, and we denote by ng became lambda ms as the set of Neumaier graphs which are edge regular with parameters v, k, lambda that contain an m regular s clique, and a strictly Neumaier graph is a non-strongly regular Neumaier graph. So Neumaier's question is, does a not strictly Neumaier graph exist? And as Martin does, we start with some parameters, seeing as we want to find the existence of a graph. We also need to know where to look. And we start with some feasibility conditions, simple feasibility conditions on the parameters. The first two here being from the fact that graph is edge regular, and the second being a simple edge counting argument. Now, if we're looking for strictly Neumaier graphs, we might also want to know when we can't have when our Neumaier graph is forced to be strongly regular. For example, any edge regular graph with parameters v, k, lambda is strongly regular if they satisfy this inequality, or a strongly regular graph with these parameters exists. I don't think this condition 2 appears in Martin's talk. And Greaves and Coulomb proved that if given a Neumaier graph that contains a regular 2 or 3 clique, then the graph must be strongly regular. Now, we can also find conditions on the parameters which hold for all Neumaier graphs, and for which there are extremal cases for strong regularity. For example, this condition Martin introduces, which I think applies to edge regular graphs in general, but Martin presents it as a condition on Neumaier graphs, says that an edge regular graph must have parameters which satisfy this inequality, and in the extremal case, when equality holds, then the graph is necessarily strongly regular. And again, we find that Neumaier graphs must have parameters satisfying this inequality. And in the equality case, the graphs are also strongly regular, and we can actually classify these graphs. So up to isomorphism, they're square lattice graphs, triangular graphs, and certain complete S-par type graphs. And so these questions, these results give a sort of idea of what questions we can ask about parameters still. So as Martin presents, we could ask non-existence questions. So given a parameter set, can we prove there's no graph with these parameters? And we can also ask for classification. We can also ask classification questions. So given a parameter set, can we classify all graphs up to isomorphism with these parameters? These questions I've given are quite vague because we can apply these to any of the graph classes we're interested in. So edge regular graphs, Neumaier graphs, or strictly Neumaier graphs. And we can apply these questions to families of graphs, as Martin's already shown us. Maybe one specific example of interest, if anyone wants to look at this one. The smallest possible lambda for a strictly Neumaier graph is 2, and this parameter set is the only parameter set for which a strictly Neumaier graph can exist with a lambda equals to 2. So maybe this family of parameters would be interesting to look at. Okay, let's move on to constructions. So Goroyanov and Shalaginov, in a paper about Deza graphs, also find 4 strictly Neumaier graphs with 24 vertices. And the first infinite family of strictly Neumaier graphs was constructed by Rhys and Kuhlen. And they were all constructed as Cayley graphs, and they could all be partitioned into one regular cliques. As Martin says, a spread of one regular cliques. And so, why are a spread of one regular cliques interesting? Well, we've already seen this, but maybe I'll give some motivation behind it, maybe a bit of a different perspective. So if we take such a graph, a Neumaier graph, which can be partitioned into one regular cliques, and then we consider an edge which is not in any of these cliques, then the common neighbors of the ends of this edge cannot lie in either of the cliques from which the vertices of that edge come from. That's a bit odd, but in this picture here, you can see. And so if we delete the edges of the cliques, then all the triangles in that edge is in remain in the graph, and the graph itself is still edge regular, just with a lower valency. And so in reverse, that's basically the Evans-Goroyanov machine, as Martin says. And these are the sort of this is the full definition of the construction, which Martin's already shown, but maybe one thing we do to emphasize possible non-isomorphic graphs is we show that we actually give the option of permuting which cocliques we stick together with edges, because this could possibly result in non-isomorphic graphs. So yeah, this construction gives Neumaier graphs and strictly Neumaier graphs when we stick more than one graph together. And as Martin's already said, this can be applied, thus is either been applied in specific cases or can be seen as a more general version of some other constructions. Let me go over some small examples. Well, so if we take two icosahedral graphs and stick them together, we get the graph that Martin nicely illustrated on 24 vertices. And actually, if we stick the edges on with different permutations, we get 4 non-isomorphic graphs with 24 vertices. We could also do the same with 2 dodecahedral graphs, and we get a strictly Neumaier graph on 40 vertices. And this is, I think, still a graph which is not contained in any known infinite family. So this one you might want to start with to extend. Now, the next one is found as the graph on 28 vertices, which Rhys and Coulon find using Cayley graphs and a bit of number theory. And we have reinterpreted this as a graph on the quotient of the triangular grid. So we take the 6 regular triangular grids, and we take a specific perfect code, and then we take its cosets and apply an appropriate quotient function to make 2 graphs, 2 non-isomorphic graphs on 28 vertices. And this approach we have been working on generalizing. So we have increased dimension. So in 3 dimensions, we look at the tetrahedral octahedral honeycomb, and we construct 8 non-isomorphic graphs on 78 vertices. And very recently, we have constructed a graph from a lattice in 4 dimensions, for which it has 250 vertices. So hopefully this will be extended to another infinite family with strictly Neumaier graphs. Again, something that Martin's already said. So all of these graphs have regular cliques with nexus 1. What about nexus not 1? Well, the only known construction is we give, and they can take. We have 2 constructions, each containing a graph with a 2 to the a regular graph with nexus the power of 2. A power of 2, positive power. And this construction starts with strongly irregular graphs, and we apply some clever edge switching to break the co-edge regularity, but not the edge regularity. So the main question, as we have already heard, is, can we find for each M a strictly Neumaier graph containing an M regular clique? I think that's one of the most interesting questions left for constructions. And in general, we are still interested in infinite families of Neumaier graphs, as there's only a handful of constructions out there. When looking for constructions, we might want to find graphs with fixed properties, for example, a fixed nexus, although we already have plenty with fixed nexus 1. And we might want to also find graphs with fixed diameter, although I think the only interesting case there would be diameter 3, which is the largest diameter such a graph can have. We could also ask if we can find any prolific constructions, and I think Martin's construction earlier gives quite a large infinite family of graphs, but can we get any more? Can we get exponentially many, or I don't know. And maybe to start tackling these kinds of questions, you probably want to start with the known constructions and how they work. At least 2, rely on number theory and Cayley graphs, and others start with more combinatorial feel. Now, this might be the only new part of my talk, which is about the computational aspects of Neumaier graphs. So the graphs initially found by Goyanov and Shalaganov were found computationally, although they were looking for laser graphs, I think. And in my thesis, I present an approach using the gap packages, great for design, and the algebraic graph theory package I've worked on, to find strictly Neumaier graphs with previously unobserved properties. For example, there's only one known strictly Neumaier graph with diameter 3. I find it computationally. There's also strictly Neumaier graphs with a unique regular clique, and there's also strictly Neumaier graphs which have a spread, and then cliques which don't lie in a spread. So let me just go over the general idea of our approach. It relies on observations of Neumaier. So given a Neumaier graph containing an M regular S clique, then we have each vertex outside of the clique, obviously by definition, is adjacent to an M set, a set of M vertices inside of the clique. But if you take the multiset of these adjacencies within the clique, then these can form the blocks of a 2 design with these parameters. And we also know that we have an equitable partition, basically. So the vertices outside of the clique induce a K minus M regular graph, a regular graph. And so with these observations, we have this general outline for an algorithm which goes as follows. So we take our favorite feasible parameter set. We then choose a corresponding design, which you can do in GAP with the design package, and you can maybe choose many designs to check. And then we construct our initial graph with adjacencies corresponding to the design and the regular clique. And we find the automorphisms of this graph. Now we're going to choose a subgroup of these automorphisms. And this might be the trivial subgroup if you want. But what we will use this for is we will enumerate all k-m regular graphs on the rest of the vertices that's invariant under this subgroup. So this subgroup is a choice you make to speed up the search, but unfortunately, if you pick a group that's too large, we may miss some possible Neumaier graphs. But at this point, we only have to do one more thing, and that's stick on the edges and see if we have an edge regular graph. So this approach is the best we have so far, and it's given us some interesting examples, but it's not very efficient, as you can see. So the first question about computations would be to find an efficient search algorithm for Neumaier graphs, or strictly Neumaier graphs. And the second question would be to develop an enumeration algorithm for Neumaier graphs with given parameters. This is obviously a lot more harder. And again, we can ask similar questions as with what we did with the constructions. So can we find graphs with fixed properties like certain symmetry conditions, the existence of a spread of regular cliques, or a fixed nexus again. And if you wanted to start with trying to tackle the enumeration problem, you might want to think about the smallest feasible parameters for which we have not enumerated the graphs, which is this parameter set 24, 8, 2, 1, and 4. Okay, and let me finish with some other areas, some other directions. So as Martin's presented before me, there's plenty to think about with eigenvalues. We can also think about connections with other classes of graphs. Strongly regular graphs are the obvious one. Other graphs like Daisy graphs, group divisible design graphs, anything's possible. We can also ask about connections with other combinatorial objects. We've seen connections with designs and perfect codes, and maybe association schemes next. And we can also throw it back to the initial motivation of Neumaier and think about symmetry conditions and what symmetry conditions what properties are forced upon Neumaier graphs when symmetry conditions are required. Okay, that's all from me. It's been a bit of a repeat, but thanks for listening.
Rhys, thank you very much for the nice talk. Answer the questions to Rhys, please.
Sure, I have a question.
Oh yeah, sure, please, yeah.
Rhys, do you believe that there will be strictly Neumaier graphs for every with nexus M for every M bigger than or equal to 1? Do you think it's just we just haven't looked hard enough or thought hard enough yet? Rhys?
Rhys, we cannot hear you.
You can't hear me? Can you hear me?
Leonard, we can hear you, but we cannot hear Rhys. I don't know why.
Ah, maybe he's muted. Okay, hi. I can't. No,
Can you?
We good?
Yeah, you're
Yeah.
good.
Hey. Okay. So yeah, that's why I put it in the construction section, because I do believe they exist. I mean, strongly irregular graphs have regular cliques with any nexus. So why not edge regular graphs, which are not strongly irregular? I can't.
You can't be heard.
Can I not be heard? Oh man. Hello. No? Now?
Yes.
Yeah?
Yeah.
Oh man. And a repeat. Okay. So what, you can hear me?
Yeah. No. I
Okay.
think you've answered
Yes, this is the answer.
Thank you for your
Yeah.
answer.
Thanks.
Thank you for your question and thank you for the answer. Well, okay. Are there any other questions, Rhys? Well, if not, then let us thank Rhys again. It was very nice, very interesting talk containing a lot of open questions. I'm sure that there will be a lot of new results in this area. Well, okay, and